Hi, I'm Jeff Applebaum. Welcome to the Cadence Innovation Theater at the 58th Design Automation Conference. In this video, we begin with Vice President Venkat Tanvantri on applying machine learning to EDA. We conclude by highlighting the impact of machine learning on simulation regression throughput. And now, here's Venkat.
Hi, I'm Venkat Tanvantri, Vice President of Machine Learning at Cadence. There are a lot of people talking about machine learning, and for good reason. We are seeing real impact from applying the technology to key high-value computational problems in EDA software. And I'm here today to share with you the applications in EDA where machine learning is producing substantial benefits. The rise in complexity of circuits and systems makes it more challenging for teams to search for optimal design trade-offs. There is a renaissance in semiconductors spurred by strong growth drivers from 5G, automotive ADAS, hyperscale computing, and industrial automation. These opportunities require more and more compute power and more semiconductors. Using advanced process nodes to squeeze every bit out of Moore's law, performance, power, and area. Let's start by considering why machine learning techniques would be useful for general EDA algorithms. EDA is full of NP-hard and NP-complete problems which are non-trivial to solve quickly and can easily result in runtime issues due to exponential time behavior. To avoid long runtimes, EDA tools use various approaches to avoid completely solving NP-hard problems. Heuristic systems based on experience can be used to guide the outcome of the algorithm, and predictive systems are used to guess the outcome without having to actually compute the answer. Designers have become accustomed to influencing these heuristic and predictive systems using design constraints such as timing margins, formal proofs, etc. However, this is a very imprecise approach, so not very ideal. It turns out machine learning is a much better technique to manage these heuristic and predictive systems, but learning about the actual design and then applying the learning to the implementation flow. This avoids the need for designers to figure out what kind of constraints to manually create. Cadence is a leader in applying machine learning technology to EDA challenges. Here, we have a broad solution using machine learning to make a major impact. Let's look at a few of these quickly. Tensilica AI platform. Here, one of the ways we make designers more productive is by supplying IP that they can integrate in their design without having to design it themselves. In this case, we supply a new Tensilica AI platform offering a range of performance and functionality options for a wide variety of on-device and edge computing applications. Cerebrus. The digital design flow is the heart of the semiconductor design, and Cerebrus is like ADAS for chip design. We'll be touching on this later in the presentation. XLA-MMO. Simulation is the cornerstone of delivering high-quality SoCs, and XLAM focuses on maximizing throughput of regressions. We will also touch on this topic later. Multiphysics system analysis. There are two activities of using AI in multiphysics systems analysis. The first one is building a surrogate model from sample points of simulations using an AI algorithm, and use the AI model to accelerate simulations to cover the entire design space. The second one is use AI ML optimization algorithm to optimize design parameters based on the simulation results. Innovus. The Innovus implementation flow uses machine learning for a variety of tasks such as pre-route delay prediction, optimization of cell selection, and so much more. And this leads to faster design convergence and better PPE results. Jasper Gold. Former proofs are attacked with multiple algorithms which are applied heuristically. ML can help improve the time to results and increase the number of successfully concluded proofs. Allegro X. Allegro X leverages an ML-based engine for synthesis of a PCB from its specifications based on constraints provided. The place and route of PCB is for the first time being assisted in automation by ML techniques. Blended into the Allegro X platform, one can initiate the design in the canvas familiar to the user and then leverage the engine to explore multiple implementation alternatives, and then finish the design for manufacturing in Allegro X design environment. The electrical analysis engines are used in conjunction with the synthesis to ensure the results are electrically correct and manufacturable. The technology is in advanced development, leveraging scalability on cloud, and is currently being supported by key customer partners in evaluating the results. Spectre X Monte Carlo. New high sigma 4, 5, 6 sigma capabilities are now available within Spectre X. It uses ML to develop an accurate surface model in order to predict extreme tail values. The algorithm produces actual spectral simulatable points, so there is no loss of accuracy here. Virtuoso. In custom IC design, the use of machine learning can be used to relay out circuits in new technology nodes, increase what-if design iteration speed, and increasing automation of the circuit layout. On the Liberate library characterizer, the earlier the design implementation is optimized for all operating conditions, process, voltage, and temperature, the better is the sign-off convergence. Liberate machine learning prediction derives quickly and accurately a complete set of PBTs and allow a better and earlier starting point to design teams, accelerating the overall design cycle. And finally, the Cadence DFM technologies. Design for manufacturing is an important sign-off step in advanced nodes. To facilitate DFM sign-off, machine learning prediction capabilities have been added to the Cadence Litho physical analyzer to effectively catch more yield-limiting hotspots and repair previously undetected hotspot patterns. It delivers up to 33% greater detection efficiency versus traditional pattern matching checks with less than 10% runtime impact.
At Renesas, we have a wide range of the products which are based on many different process nodes depending on the application and performance requirements. We always want to use the most cost-effective approach in a product, so we are often changing the design methodology based on the latest foundry offerings and required targets. This means that due to these many different chip design configurations, Renesas must continuously update the implementation flow for our designers. Using the distributed computing capabilities, servers did about 100 runs and quickly converge in the flow that results in over 15% power reduction. We use a new 12nm high-speed CPU design project to see how serverless could optimize not only the implementation flow but the floor plan. Based on about 50 runs, serverless generated a new flow and a new floor plan that delivers better performance by over 10% for this high-speed CPU, saving us many months of the manual floor planning and flow tuning effort. This is exactly the kind of productivity benefit we are hoping to achieve by working with Cadence on the Cerebrus technology. In addition, we realize with machine learning technology such as Cerebrus, our designer will be able to drive the design process at much higher throughput without running the experiment. We are now actively deploying the Cerebrus in production for critical and important chip design projects at Renesas. We believe Cerebrus will provide the kind of engineering productivity, design performance, power results, and the breakthrough we need to ensure success for next generation of Renesas products.
Your designs are getting bigger. Verification is consuming thousands of CPU hours. And verification closure is taking longer than ever. You need to improve regression efficiency to increase your throughput and finish on time. Xcelium ML applies machine learning to reduce simulation cycles up to 5 times, while achieving the same coverage and accelerating verification closure. Cadence, computational software for intelligent system design.
At Cadence, we empower engineers at world-leading semiconductor and systems companies to create intelligent and highly differentiated electronic products that rely on the most advanced semiconductor devices. From consumer products like mobile devices and autonomous driving to next-generation hyperscale computing, the technologies of the future will be integral in our lives and intelligently connected. Electronic design automation, EDA, has always been at the forefront of breakthrough design, driven by advanced computational software, the bedrock of what Cadence delivers. With the explosion of big data and massive computational workloads, it's more important than ever to leverage proven software, computational in nature, that includes best-in-class design, verification, IP, and system analysis capabilities. Recent advancements in silicon design and computational software address these design challenges head-on with an intelligent dimension. The difference centers on select key innovations: integration and co-mingling of previously independent design, analysis, and implementation to achieve optimal results. Partitioning and scaling of computation to thousands of CPU cores and servers. And the introduction of machine learning to improve and harness design heuristics for system optimization. Cadence, computational software for intelligent system design.